The last section basically involves putting together everything we've done already. We'll do a couple of examples. There's nothing new here, but we'll work. Actually, no, that's not true. There is one new thing that we'll get to at the end. The whole purpose of no, I shouldn't say the whole purpose. One of the main purposes of mathematics is to be able to use math to make predictions. You know, weather forecasters use mathematical models that pertain to weather to make predictions about the weather, either in the short term or the long term. Sometimes they're good and sometimes they're not. And that kind of gets to the point of what we're doing today. Today, we're going to look at some situations, and we have to kind of try to guess at what the models for the situations are going to be and which one we think is going to fit the best. So we'll start with a linear model. So this is something that you could have done and had in grade 9. So we've got Mark, who uploaded a video to YouTube. In 2 days, the video had 165 views. Find an appropriate function to model the situation. We'll assume it started with one view, you know, either Mark or a friend viewed it. The question is, when will the video reach 1,000 views? So again, this is something that you might want to try to predict. You know, if Mark were a serious YouTuber and trying to get some money off of this, he'd want to know how quickly his viewership is going to grow so that he can figure out how much money he could potentially make. Well, you have to start somewhere, right? Like, you're not going to become a serious, your first YouTube video is probably not going to get 1 million hits, but views.
I don't know if you say fine calculation.
So we'll start with a linear model. Is that okay? You guys able to see that? I'll give you a minute to write it down, and then we'll move on from here. I used to actually have the classroom set up as basically a U shape and then another U shape in the middle, so it's kind of reminiscent of those days. Oh yeah, a little yeah.
Brendan said he's mad at you because you cut him off yesterday in the park.
Did I? Oh. So I've just taken the information here. I think I got the important information. The video started with one view, his view, probably. It's measured in days. Thanks. I should probably put that in here. That'd be pretty good. How do we create a linear model for this situation? Yeah, we can use an x. What else? What does a linear function look like? It's a straight line. So what does the equation of a straight line look like? Yeah, there we go. Y equals mx plus b. Yeah. How do we find the slope? Here's the rise. What is that? 164. Here's the run. I haven't gotten that far yet. Hang on a minute. What's that, 82? And then, yeah, we need the b value. So remember, the b value is the y-intercept. It happens when x equals 0. When x is 0, y is 1. So that information was given to us. Right here. The b value is the y-intercept, where x equals 0. So, right, and that's, so John's saying I don't think it's going to go up at a constant rate. That's something that we don't really know. So we kind of use this information and we kind of can either, well, I mean, there is some sort of, I don't want to say guessing, but some thinking that happens there about, does this kind of model make sense? And it might make sense for a little while, where at first you know have a couple of views a day. What would be different if I told you that this video went viral? What would be different about the equation that we choose?
Yeah, the amount of views in a day, so that's M will change.
Yeah, possibly M will change, but typically with a viral video, you kind of get a few. It would probably be an exponential where it grows really quickly, and then as Josh said, you probably kind of levels off after a while, right? After a certain point, people stop watching the video because either they've seen it or they're just not interested. So according to a linear model, we might say that the number of views, I'll just use V for views, is equal to 82 times the what am I trying to do here? Number of days. I'll use a D here for days plus 1. So using this model, we can make a prediction about when the video will reach 1,000 views. Where does that 1,000 come into play here? Yeah, it's the number of views. So we can put 1,000 in here, 82D plus 1. And now we can solve for D. Subtract 1 from both sides. Divide by 82. And we can come up with some value there. I don't know what it is, but. What is it?
12.1. There's a lot of other numbers.
Okay, well, that's good enough. So what does this number mean? Yeah, so if this video is really growing at this rate, then come the 12th day, it should have about 1,000 views. And again, we should answer that with a sentence here. On the 12th day, he should have 1,000 views. Now, John said earlier that he didn't think that this is how it would grow. So a second way model that we could use that you guys are comfortable with or familiar with is a quadratic. We should be able to model this situation with a quadratic model. Why? That's a good question. Why? Why do you ask that question, Leslie?
Well, because the quadratic, like
right, so there would be like a maximum or minimum? Right, but could it be a parabola where we just look at half of the parabola, say? So day 0 is here, kind of like this. So it's not growing linearly, it kind of grows slowly at first, and then as word gets out, it starts to grow faster. Yeah, definitely. Yeah, sure, it could go like this too, right? Yeah. Well, I think what John's suggesting is that it kind of looks like this, where it grows a little bit more and then either stops or it kind of just grows a little bit more. So this might actually be a good model for a certain chunk. And we kind of looked at this before where we said, hey, you know, this model is good for a certain percentage or a certain amount of time, but it's not good all of the time. I remember doing an example like that. I can't seem to think of what that example was. But, and that's possible too, where the model might be really, really good for a certain number of days, but after a while it may not be. I think in this situation, it might actually make more sense to look at this than something like this.
list is based on how many people watch it. So if you start off with one person, you're not going to be at the top of the list, you're going to be lower. So as soon as you have more views, more people get the chance to actually see it.
Thank you. Yeah, and we can do an exponential as well.
Like when we write it, how do we write it so that we know there isn't a part like in the negative? Yeah.
Yes, I do get what you're saying. We could make it so that. So what you're asking is, how do we make it so that it's just this part? Well, it doesn't make sense for us to talk. You know, if we just released the video today and today's day 0 and our parabola seems to fit, except for over here, well, it doesn't make any sense for us to talk about what happened in the past, right? Obviously, it had no views when I didn't make the video, right? So we could, yeah. So in this case, when you put in a negative number, you say, well, that doesn't work. Well, of course it doesn't work. It doesn't make sense to have views on the negative days when the thing wasn't even created. Is that okay? All right, so how are we going to do this? We fairly easily came up with a linear model. How are we going to come up with a quadratic model? You do it in grade 10. The thing about grade 10 when you do it is that you typically know some information, like the vertex and one other point. In this case, we would have some information. And if we say that the graph is going to look like this, if we say the graph is going to look like this, what's the vertex here? Yeah, the vertex is at 0, 0. Oh, yeah, sorry. Yeah, you're right, because we were, thank you. That's how I drew it, see? Just above the, no. Because we didn't draw it, we didn't start with 0 views, we started with 1 view. So using that same table of information, we can then use the quadratic equation, quadratic function to find a value. You don't do a lot of this in grade 10 or 11, but you would do a little bit of it, where typically in vertex form, where you know the vertex, and then you kind of find other values. So that's one thing that we could do. The other thing that we could do here is we could actually use technology. No. And we can do a quadratic regression. In grade 9, you do line of best fit, quadratic. And in grade 9, we tell you that the line of best fit is you kind of line your ruler up and kind of figure out where the center is, you know, with points, as many points as possible on the line, equal numbers above and below. And that's kind of good enough as an estimate. There is actually truly one line of best fit. And those of you that are going off into the sciences next year, you will spend a lot of time finding the equation of that one line of best fit, especially if you're doing chemistry and biology, I guess, and physics. You'll do a lot of these sort of calculations where you actually figure out the equation of line of best fit. We used to do it by hand. I don't know. Maybe now it's just all done on text. I would certainly, you know, to plug this into a graphing calculator and get it to give you the equation is very easy to do. So maybe that's something that's available to you guys that wasn't available way back in the dinosaur days. So let's do this. Let's do a quadratic regression. A quadratic function can look like a whole number of things. It could look like this. That's standard form. It's not very helpful if you know the y-intercept. That's this value right here. So if we're assuming that, I mean, we are saying that the y-intercept is 1, we could plug that in, but that's not very helpful to us because it doesn't give us a lot of other information. The other form of the quadratic that you might remember is vertex form, which looks like this. We can plug in the vertex in for h and k, and then if we know one other point, we could sub in the x and the y values and solve for a. And we can do that, yeah. So let's go ahead and do it. I guess the x coordinate of the vertex was 0, so x minus 0 is still 0. And k value was 1. And from this point, we can substitute one of the points at one other point in. Yeah, so h is the, sorry, not at 0, but h is the x coordinate of the vertex. So this point right here, the lowest, to which we're assuming this is, has the coordinates of h and k. Yeah, yeah, vertex form, right? So yeah. Lowest or highest point, yep, depending on how the graph opens. Yeah, this is like all of high school all reviewed in one example. Did the grade 9 stuff, the linear, the quadratic is the grade 10. I guess we kind of, the exponential you do a little bit in grade 11. So the only other point that we have somewhere up here is this point 2, 165. So x is 2, y is 165. And then we can solve this for a, and we'll have an equation that we can use. Was that 41?
Yes.
Really? Oh. I actually did it in my head as you guys were typing into your calculator and thought there's got to be an easy way because I didn't do it very easy. Like this looks like it should go easily. So I could have just done 16 divided by 4 is 4 and 4 divided by 4 is 1. I didn't do it that way until afterwards. I thought, oh, I should have just done it that way. So then the equation looks like this. What did we say? It was the number of views is equal to 41 times x. There was no shift left or right, so just x squared. And then the plus 1 went over here. So we've now come up with an equation that we can use to represent the situation. And if we wanted to figure out how long it would be for 1,000 views, we can plug in the 1,000 for v. Solve that. Whoops. Divide both sides by 41. I'm not even going to try this one, Aaron. $24.3? What is it? 4? Okay. And then we take the square root of that. A little less than 5. 4 point, what's that, 4.9? Yeah, one decimal place is fine. What does this number mean? Yeah, until you get it to 1,000 views. And we can kind of check our results, right? Had we somehow made a mistake and x here was bigger than it was with the linear mod, sorry, smaller than it was, sorry, let's try that again. If the number of days was bigger than it took to get to 1,000 views with the linear model, we probably did something wrong. The quadratic grows faster than the linear, so this should actually take fewer days. So therefore, it should take about 5 days. That's an excellent question, Aaron. We don't know which one's right. We kind of have to make a guess at how we think this thing's going to grow. So do we think it's going to grow linearly? Do we think it's going to grow like a quadratic? And you kind of take an estimate and kind of see what you think is going to happen. That's why sometimes the weather is so wrong, is that they have these models. They use, when forecasters use models, they use computers a lot. So the computers do a lot of the number crunching and stuff. But they say, you know, it looks like there's this great big storm system in the middle of the US, and it's kind of headed towards Canada, and it might go this way or it might go this way. They have to make some judgment about what they think based on all kinds of information and choose one. And sometimes they choose the totally wrong model, and we get, you know, this forecast for this ridiculous amount of snow, and it turns out we get none. It's because they chose the wrong model. And that's what happens in real life, is that you're trying to model a real life situation with mathematics. It's not to say that the models are wrong. It's just the one that you chose maybe didn't turn out. So if we were trying to predict the number of views here, how long it would take, just based on the 2 days, we don't know how it's going to turn out. The only thing that will tell us is time, that when 5 days goes by, we can kind of look back and say, oh, geez, you know, it didn't grow quite as well as we thought. Maybe this video is not nearly as good. And then we can check again, you know, after 12 days, maybe it does grow. Or maybe after 12 days, it kind of, that's it. Maybe the views that it was going to get on day 2 is kind of where it plateaus and it just stops at 165 because nobody's interested in the topic anymore. So on a test, if I ask you, probably on a test, I would actually ask for both of the models, and then I would ask you to provide some justification about which model you would choose and why. And yeah, so you might say, I don't think it's possible for this video to grow or to get as many views. I don't think it's going to grow at a, according to a quadratic model. I think it's going to grow linearly. Or you might say, you know, typically videos get a few hits at the beginning and then they, you know, make it onto some of those lists that Joss was talking about, and then they tend to grow a little bit faster and so on. So there, I'm not saying, and I know, Leslie, this is probably driving you crazy, because there is no right answer, you know. There is no right answer for a weather forecast until after the fact. Then we can make a judgment.
So for that answer, can I just say, well, matter after the fact anyway? Yes,
I would like you to make some justification about why you think one of them is a better model than the other. Leslie's clearly not going to be a weather forecaster.
There has to be a right or wrong answer.
If you don't like either of them, then you can go to the third one. So to answer your question, Leslie, if you don't like either, you could go to option number 3.
What if we don't like the third one?
Will you make us do all 3, or will you say show this in 2 different ways we can choose from the 3?
That would be a good idea. Because 3
Maybe.
would be a lot, right?
3 is a lot, you're right, unless that was the whole test.
Let's not.
Oh,
No, because then
let's
we
do
can
it then.
choose like 2 of the 3 that are stronger.
Oh. Maybe you should choose one that you're not so strong at so that you could improve, and then come exam time, yeah. How do we do an exponential model? Yeah, y equals a times b to the x. Just a reminder, here's the data that we had. This was the number of days, and this was the number of views. So somehow we have to take this information and turn it into this. How are we going to start? Yeah, so 1, remember that in the exponential function, the a here is the initial value. So we know for sure that the equation is going to look like this. I suppose we could just leave the 1 out. How do we find b? Hey, there we go. We have an x, we have a y. Let's plug it in and find b. Sub a point, sub in a point. To find b. We only have one other point.
Would you sub in 0 and 1?
Well, here's what's going to happen if we sub in 0 and 1. I'll show you what's going to happen. This is true, right? B to the 0 is equal to 1, so 1 equals 1. That's a true statement. There's nothing wrong with that statement, but it doesn't help us find x, right? So make sure you do sub in a different point, and in this case, we're going to sub in the point 2, 165. Right. It's kind of like when you, I mean, the same thing happens when you come up with an equation y equals mx plus b. If you sub in the y-intercept to y equals mx plus b, you get that the left side and the right side are the same, but you don't actually find x. Now what? Yeah. What's that, 13.1? Oh, yeah, you're right. I went the wrong way.
The 5
12.4? 12.5.
12.8.
Oh, 12.
Yeah.
Thank you. Okay, sorry. So now we have a b value. B in this case is 12.8. So our equation then could become that the number of views is equal to 12.8 to the x. And again, x is the number of days. Sorry, I didn't need to write views. I just need to write v here. And then again, we can solve this the same way that we did before. How long is it going to take to get to 1,000 views? And then we can solve this equation, this exponential equation. Good review here. Yeah, we want to pull that exponent down, so we'll take the log of both sides. The log of, let's try this again, 12.8 is equal to the log of 1,000. Again, with the logs, we can pull this x out front. It doesn't matter because we're not actually doing any trig work here. So the radians and degrees only affects the trig functions, the sine, the cosine, and the tangent on your calculator. From here, we can divide both sides by the log of 12.8. 2.7? Okay. So it will take about 3 days. It doesn't matter. Either one. When we're talking about a day, 2.7 or 3, doesn't matter. And again, maybe this model is accurate and maybe it's not. And if on a test I give you this information and I ask you which model do you think is best, there's no right answer provided that you can provide a reasonable explanation for your answer. So if you say, I think the linear model is best because it grows the fastest, it's okay that you gave an answer, but your justification is totally off. So you need to make sure that your justification matches your calculations, right? The exponential looks like this. So it starts off slowly, and then it goes like this. Oh, sorry. Yeah, sorry, this one. Well, this. Well, according to the exponential model, based on the information that we have, because nobody saw it, nobody knew about it.
No one cared about it.
Got to get the word out first, and then.
That could just be the population of one school, one big school, right? One person sees it in school and tells them which
I
branch.
feel like the linear one would be less accurate.
How come?
It's like it's not gonna go off that exact same representative day.
Right, it won't be exactly the same, and we only had 2 points to work with. So ideally, what you want to do is you want to get more data here, and then you want to fit that data as best you can. So find the line of best fit or the curve of best fit, and then find the equation of that line or curve. And again, choose which one you think is going to be the best. Is that okay? If I had to guess, that's what I would guess too. Erin's putting that down on her test now. Yeah. So here's the fourth method, which is, I said there's one new thing that you're going to learn today. Here's that new thing. This model is called what's called a logistics model. And it's actually probably the more accurate model because with a logistics model, you get what's called an S curve or a S-shaped curve. With this model, you get growth that looks exponential to start with, and then it levels off. And that's probably what's more likely to happen. You're going to get lots of views at the beginning. We talked about these viral videos. Once you've seen the viral videos and you've seen the cat do whatever 1,000 times, eventually you're going to get bored and move on to something else. This would happen with disease as well. If we look at the spread of a disease, it generally grows pretty quickly and then levels off for one of two reasons. Either the disease is under control or the population has been eliminated. I mean, at some point it has to level off, right?
Then I go home.
So what would you call a model that you
A logarithmic model. So there's an equation that goes with it. I mean, I guess there were equations that went with the others. For a logistic function, the equation is P at t. So P at t is the population at a given time, is equal to C over 1 plus A times B to the t. We're going to kind of work through an example here so that you can see where those things all play out. C is called the carrying capacity. So it's kind of like the maximum that the function would get to. This would actually be an interesting, if we could somehow get the stats on this would be an interesting study to do over the next couple of years. Our school board just last week, I feel like, announced that they changed the head lice policy. I don't know if you guys heard about this. It used to be that if you had head lice, you had to be sent home because they were worried about that spreading. Anyway, some health organization, health units maybe, basically did a study and said, it was a pediatric society, and said there's no reason to send kids home for having lice. You know, it's not a health issue for the kid. Like, the kid is still able to be at school. It's not a like disease that's going to infect other kids. Anyway, so that's something that just recently happened. It would be interesting to see what the carrying capacity of lice would be in students in the school board as a result of this sort of change in policy, and see whether there are going to be more cases, more students with lice, or if it's just going to stay the same. Is that okay? Is that too far? Yeah, it's a little bit different, but yeah. A and B are different in this situation, though. They're just values, and the one thing about this model is that you need some way to estimate what you think the total will be. So in the example that we did with the video, we need some estimate of how many views we think this video will actually get. Yeah, T is time. As soon as you guys get that written down, we'll actually go through and we'll actually figure out what all the different values are in this equation. Plug them in, and then we'll have a function, and we can use that function to model the growth of the videos. You guys have this written down already, but I'm just going to write that data down so I don't forget it. It's a good question. We'll look it up when we're done. I think attains is like reach and hold, whereas obtain is just getting there. Like, the key here, so the key for the logistics model is that we need the 2 points that we had for the other two models, but we also need this carrying capacity, some kind of estimate about the carrying capacity. So on a question, if I were to give you a question like this on a test, I would have to either ask you what you thought the maximum carrying capacity is. I probably wouldn't ask you what you thought the maximum carrying capacity of some. bacteria. Yeah, so that's a great question, Tiffany. So on a test, a question like this, I would ask you how many views in total do you think this video is going to get? But then I could get, 25 different answers or 22 different answers. So I'm likely to tell you, hey, it's estimated that this video is going to get a total of 10,000 views. Okay, so C is the carrying capacity. This C is the carrying capacity, which is the total maximum that we think is ever going to happen. So in this case, the population, or in this case, I suppose we could use V since we're talking about views and not population. The number of views over time is going to equal that 10,000 divided by 1 plus A times B to the T. In this case, we have some values that we don't know, so we're going to have to do some calculations. A little bit of manipulation here. We know that at time equals 0, that there's one view. So we can set time equal to 0, we can set the view equal to 1, and that will leave us with an A that we can solve for in this equation. So our first sort of order of business here will be to sub in the point 0, 1, and solve for A. What's that? That's a good question. As soon as I put a 0 in for T, B is going to disappear, right? B to the 0 is just going to be 1. So we're going to come back. We're going to have to find B. We'll have to do it in another step, though.
What if you don't give us, like, what if there is no point?
I would probably give it to you because you kind of need to know where it started. Kind of like the exponential one. I mean, you could do it if I didn't give you that initial value. It just requires a little bit more work. That we have to find. It's just a number, and we have to calculate it. So we actually don't know. No. This not a vertex, but this was the point where x is equal to 0 because, or in this case t. Sorry, we're gonna plug that 0 into here, which is gonna give us a 1. What's that? It's not really it's the y-intercept.
So do you always use the point where x is 0?
Yeah, yeah. If not, then you have two equations with two unknowns, and there's a lot of extra work. I think we'll stick with keeping to the examples where where I give you the y-intercept. So the views we said was equal to 1. We had 10,000 as our carrying capacity. 1 plus A we don't know, but we're going to sub in a 0 for T. Which one? This one? This one came from here because this is the number of views at time equals 0. Remember that this is time and this is the views. A couple of ways that you could solve this. Some of you might not like this, and I'm not suggesting you have to do it this way. But you can solve this by, I don't want to say common sense, but maybe by inspection. You kind of look here and you say, oh, 10,000 divided by something has to be 1. What does the bottom have to be? It has to be 10,000, but we're going to add 1 to it. So what do we add 1 to and get 10,000? 999. So A has to be 999. Sorry, 9,999. It's too many nines. Which reminds me of another question I'll ask you later. So you can do that just by looking at it, or if you want to, you can go through the process of multiplying both sides by 1 plus A and then solving for A. Is that, I don't know, you guys choose how you want to do it.
Will the examples on like will test questions be that simple to where it's common sense, or will we?
Well, these ones are going to have to be something. I mean, you're always going to have a fraction. You'll have a 1 plus A in the bottom and some number over here. We'll go through the process. So I'm going to multiply both sides by 1 plus A to get rid of the 1 plus A in the denominator. Thank you. So we just found A. If we sub the other point into the equation, we should be able to find B. So the other point was 2 and 165. So if we have 165 views, carrying capacity is still 10,000. 1 plus A we said was 9,999 times B squared, right? Was it 2? Yeah. So this was subbing in the other point. So the 165 goes in for the number of views. 2 goes in for the B value. And now we can go ahead and solve for B. Multiply both sides by the denominator. Distribute the 165 or divide by 165, whatever you prefer. Just divide it? Sure, yeah. Good, because I can't do that. I can't do this math in my head either. So what's 10,000 divided by 165?
60.6.
We can subtract 1 from both sides. Divide both sides by 9,999. I'm going to, I'll take it to, sure, 6. And then take the square root. Yep. So we found A, we found B. We can plug them back into the equation. One, 2, 3, 4 times 0.077 to the t. And then if we wanted to figure out how many views there were, what did we do before? Oh, it was 1,000, right? How long did it take to get 1,000 views? We can plug 1,000 in here and just solve. But there's the function that would model that S-curve. So if we were to graph this, we would very much get one of these where it grows quickly and then levels off. Leveling off, where does it level off? Yeah, at about 10,000.
We can't do 9,999 times 0.077 first, right? We have to do
Yeah, that's a good point. Thanks for bringing that up. Yeah, order of operations is key here. If you're going to sub in a time, make sure that you do the 0.077 to the exponent of that time before you do the multiplication by 9,999.
When we use like the 165 or the 2,
Yep.
like we use that point, will we get a different equation if we use a different strategy?
No, you'll get the exact same equation. Yeah. Any other questions? I see that the work that I suggested here is different from the work that I suggested over there. But sure, let's do 1 to 6. And that's it. That's the last lesson of the semester. Tomorrow is Friday, isn't it? Oh my. Yeah, tomorrow's Friday, so we'll review tomorrow. And Monday, we'll do the test on Tuesday. And then the last bit, we'll spend some time getting ready for the final exam. Wrote your exam today. A little bit shorter than I would normally make it.
What is the test?
The exam. About 130 marks.
That's terrifying.
Normally I would have about 140, but it was 130. So.
Oh, no.
Terrifying, but maybe good. Aaron suggested the other day that if there are more marks, then every time you make a mistake, you don't lose quite as much as a percentage.
Stop. Every time we lose a mark.
Our class out of 84.
Chemistry